Okay, I'm gonna do a couple of videos about partial fractions. So you may have seen integrals of the following form. So we've got an Rx, which is some polynomial, and we've got a Qx, which is another polynomial. And these integrals are difficult. And what we have to do is we often have to resort to what's called partial fractions. So I'll just give you an example. Yes, there's an example of our Rx is x squared plus 2x minus 1, and Qx is this 2x cubed plus x squared minus 2x. All right, and we call this thing a rational function because it's two polynomials divided by one another, and the higher degree polynomial is on the bottom. Now, there are several possible cases for different Q and R's. This example here is one of the simplest cases. Essentially what we want to do in this case, note Qx is firstly we want to factorize the denominator. That's our first step in all of these partial fraction things. And then we decide on a course of action based on how Qx factors. Distinct, linear. Okay, so distinct. No factor repeated. That's what distinct means. Linear means that all factors look like this, not like, for example, cx squared plus d. All right, so this would be a nonlinear factor. So again, we're taking linear to mean no powers or functions of the things. And this thing only works for polynomials, so if you see a sign in the denominator, you can't, or a cos or any other sort of more complicated function, you're not going to be able to really apply these techniques. If we have, as we do in this case, distinct linear factors, we call this case 1 for partial fractions. And we write our factorization, some constant, over the first factor of Q. So this is the factors of Q. Just make that clear. All right, and there could be n factors of Q, depending on how big Q is. Now, up here we've got Q is a third order polynomial, so we expect 3 factors. The problem or the trick is that A1, capital A1, they're all unknown. We have to find them such that the right-hand side equals the left-hand side. Now, the left-hand side is our integrand, so we know what that is. So there is enough information, because we know what the factors of Q are, there is enough information to determine these constants. It's just a bit tedious. So referring back to our worked example, I'll show you how to do that. So I'm not actually going to go ahead and do the integration. The integration's not important. Once you've got all these factors, the integral's trivial. I'm going to show you how to do this decomposition. Right. I'm just going to write down the factors. Okay. Incidentally, to factorize the denominator, all you've got to do is divide. Notice there's a common factor of x, so you can pull that factor out. Then you'll get x into 2x squared plus 3x minus 2. You solve that quadratic. All right, so that should be factoring polynomial should be high school stuff. All right, so now our partial fraction decomposition. All I'm doing is taking the factors of my Q, and I'm writing it out in the way that we proposed. Now, what I've got to do is I've got to work out equations for A1, A2, and A3. Now, there's two ways to do it. I'm going to show you the shortcut fast way, and that is multiply through by the denominator. Like so. And now note that this equation must hold for all values of x, thus must hold for any particular choice of x. So that is, if I stick in any old x value into this must be true. Therefore, I can be clever and select x values that simplify the process. So for example, one of the simplest x values you can think of is x equals 0. That means that on the left-hand side of the equation, I have minus 1. Here, that's 1. I've got A1, 2x disappears, so I've got a minus 1. X disappears, I've got a 2. AX2 times 0 is 0. And the same for A3. So now what I've done is I've managed to pull out an equation for A1. So now I know what A1 is equal to. What I can do is I can exploit the fact that one of these things, I can set, say, x equals to minus 2. that gets rid of this factor. My A1 term disappears, my A2 term disappears, and my A3 term survives because it doesn't have this this x plus 2 factor. So by carefully choosing x values that are the roots of Q, right, I can deduce A, 1, 2, and 3. All right, so I'm just going to go ahead and do that. X equals minus 2 implies 4 minus 4 minus 1 z equals 0 plus 0 plus A3 into minus 2 minus 5. Okay, so A3 is looking like minus 1/10 when that all simplifies out. And finally, we've got the other root, which is x equals 1/2. And if we do that, we should find that b equals 1/5. So let me just, I'll zoom out because I can't see anymore. A1, that term's going to disappear because it's got a 2x minus 1 in it. A2 is going to survive because it doesn't have that term in it. So that's going to be 2.5. Okay, and so this fairly obviously implies A is 1/5 when you cancel out the factor of 1/4. Okay, so that means I've actually decomposed this awful expression. X squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. That's equal to right. All I'm doing now is I'm just back substituting into my original expression, which is off the page. I'm obviously just copying it down from where I was. A1. Okay, and if we go back up and see, that's our initial expression. So that's just copying in our values, and we have completed our partial fraction decomposition for this case where the denominator was a product of non-repeated linear factors.